Hello chemists, this is Ms. Placino and you are watching screencast 13.7 on balancing redox reactions. In this lesson we're going to talk about how to balance redox reactions in acid. So these are more complex redox reactions than the relatively straightforward single replacement reactions we've been looking at so far. So this is more advanced, it's definitely going to be more challenging, but if you get down the routine, you kind of understand the procedure, you'll see that these aren't really as nasty as they look. Okay, so the technique we're using is called the ion-electron method of balancing. And it turns out that many redox reactions are going to take place in acidic environments. Now we talked about acids and bases previously. When you hear the word acidic or you think of acids, hopefully you associate that, especially areneous acids, with a specific ion. If you're thinking H+, you are correct. All of our acids and bases, again, areneous acids and bases, are aqueous in nature. So in addition to H+ ions, what other substance is going to be present in all of our acidic solutions? You might be thinking water. That's what aqueous means, dissolved in water. So we're going to have H+ ions and H2O molecules floating around in solution, and we're actually going to use those to balance an equation, like it says right there. You have to keep in mind when we're using this technique to balance that all equations must be balanced for three things: mass, charge, and energy. Mass is usually pretty straightforward for most people. We've been balancing equations for mass, in other words, making sure there are the same number of atoms of each element on both sides of the equation since very early on in the semester. We've looked at energy previously when we were talking about reactions being exothermic or endothermic. And more recently, we've been looking at charge. We know that in a redox reaction, electrons are lost by one substance and gained by another. So we're able to add electrons to our reactions to make sure that they are balanced for charge as well. All right, so let's get into an opportunity to use the ion-electron method of balancing. Okay, this might look kind of nasty at first glance. The first thing you want to do is assign oxidation numbers, and that's how you're going to know that this is a redox reaction. So let's go ahead and do that. Now the oxygen is usually -2. I've got -2 times 7, that's -14, and I've got a total of a charge of -2. So I need a +12. I've got 2 chromiums to do that with, so I've got +6. Oxygen again, usually -2. In this case, nitrogen looks like it would be a +3. Chromium 3+, okay, that's an easy one. And now I've got the nitrate ion, again, oxygen at -2. Nitrogen, in this case, has to be a +5. So based on what we talked about previously, how do you know this is a redox reaction? Well, when you look at it, you've got changes in oxidation states. Chromium goes from +6 to +3, and nitrogen goes from +3 to +5 as we move from reactants to products. So even though this does not look like the traditional single replacement reactions that we've looked at so far, this most certainly is a redox reaction due to the fact that we see changes in oxidation states. So we've already taken care of this. First thing you want to do, assign oxidation numbers to each elements in the equation on both products and reactant sign. We've got to identify the elements that are involved in the redox reaction. Hopefully it's pretty clear to see that nitrogen really doesn't experience any changes in oxidation states. It's always a -2. Chromium and nitrogen, however, do experience changes in oxidation states. Oh, I did have them show up. There we go. That's a little bit neater to look at. So again, chromium, nitrogen, chromium, nitrogen, we definitely see changes in oxidation states. We're going to write out the half reactions. When we do this, we want to balance elements that are not hydrogen or oxygen first. Hydrogen and oxygen pose their own unique problems. Then we're going to try to balance out our oxygen atoms using water molecules. Since this reaction is taking place in an acidic medium and acids are aqueous, it is safe to assume that water molecules are floating around, so we could use them to balance. Inevitably, as you add water to one side, you're going to be adding H to the equation. So we're going to balance out the hydrogen atoms with H+ ions. Makes sense? We've got an acidic solution. And finally, there's a good chance, actually there's a 100% chance, that the charge is not going to be balanced on both sides of the equation. So we need to use electrons to balance out the charge. So let's go ahead and try that out. So I'm going to pull up your notes. Okay. So I know, and I know you've seen this a couple times now. I'm going to start with my chromium reaction for no particular reason. So I'm going to take the whole substance, in this case the dichromate ion, and I know that chromium and chromate turns into just the Cr3 plus ion. Now again, the first thing I want to do is balance elements that are not hydrogen or oxygen. Well, that leaves me with chromium in this example. I've got 2 chromiums on the reactants. I only have 1 on the products. It's a little bit smaller. So I'm going to put 2 chromiums over on the product side. Now I'm balanced for chromium. Up next, I have to solve my oxygen problem. On the reactant side, I have 7 oxygens. If I add 7 water molecules, I've now taken care of the oxygen problem. However, I've created a new problem. I now have 14 hydrogen atoms on my my product side. I don't have any on my reactants. Because this is taking place in acid, it's perfectly okay for me to add 14H+. Okay, so we should be balanced for mass now. I've got the same number of chromiums, hydrogens, and oxygens on both sides of the equation. Up next, I check for charge. So I've got plus 14, and I've got a minus 2, so that's a plus 12 over on the reactant side, and just a plus 3, because water is neutral on the product side. So plus 12, I got 2 times plus 3, so that gives me a plus 6 overall. So in order to balance this out, I need to put 6 electrons on the reactant side. Now I've got the correct charge. They're balanced. Let's try this again with nitrogen. Uh-oh. First thing, check and make sure that you balance everything that's not hydrogen or oxygen. In this case, it must be nitrogen. I've got 1 nitrogen on the reactant side and 1 nitrogen on the product side. Balanced. Up next, I need to balance for water. I need to balance oxygen with water. I've got 2 oxygens on the reactant side, 3 on the products. Sounds like I need just 1 water to balance that out. Next, I take a look at hydrogen. By balancing the oxygens, I've added 2 hydrogens to the reactant side. I now have 2 hydrogen on the product side as well. So I'm balanced for mass. Let's check charge. 0 plus minus 1 gives me a negative 1 on the reactant side. Minus 1 plus 2 gives me a positive 1 on the product side. In order to balance this for charge, I need to add 2 electrons to the product side. All right, and those are my 2 half reactions. Those are considerably more involved than the half reactions that we were writing earlier this unit. You've got water molecules, hydrogen ions, and electrons, as we did before, to get this balanced. So this is definitely more involved than what we had been doing. All right, to get back to the notes, the third step is to combine the half reactions. We know oxidation plus reduction is going to give us our full redox reaction. We have to make sure that the number of electrons lost is equal to the number of electrons gained. We have to conserve charge. So I see 2 electrons being lost in my oxidation and 6 electrons being gained in reduction. The way to address this is to multiply the entire equation by a coefficient, or by a number, so that I can get my coefficient of the electrons to be equal. And if we've got substances present on both sides of the equation, they're going to cancel out. I'll show you a little bit more about what we mean in just a second. Let's get back to your notes. All right, so as I take a look at this, same thing as before. I've got 6 electrons gained, 2 electrons lost. Let's put this in a different color. I'm going to take this entire second equation and multiply it by 3. By multiplying by 3, 3 times 2 gives me 6 electrons, and now the total number of electrons lost will be equal to the number of electrons gained. These questions do tend to take up a pretty decent amount of space. There we go. We're going to combine them. For the sake of making things a little bit easier, I'm going to erase this initial equation just because I don't need it and I don't want it to get in the way. You can draw a line through yours or however you're following along. Okay, let's use black to cancel stuff out. I'm going to add them up. Got 6 electrons on the product side, 6 on the reactant side. They cancel. H pluses can partially cancel. I've got 14 on the reactants, 6 on the products. Sounds like it would overall be 8 on the reactant side. I can do something really similar with the water. 3 waters, 7 waters. That would reduce down to 4 waters. And I think at this point I don't have anything left to cancel. So I get a final equation. Oops, scroll up a little bit. 8 H plus the dichromate ion plus 3 nitrite ions gives me 3 nitrate ions plus 2 chromiums, chromium 3 plus more specifically, plus 4 H2O. Wow, a lot of work, very complicated looking balanced chemical equation. You should always take the extra minute and make sure that you are balanced for mass and for charge. So let's do mass first. I've got 8 hydrogens, 4 times 2, 8 hydrogens. I see 2 chromiums, 2 chromiums. Good. I've got 7 plus 6, so 13 oxygens. I've got 9 plus 4 on my product side. Again, that's 13 oxygens. 3 nitrogen, 3 nitrogen. I am balanced for mass. Let's check charge. On the reactant side, I have 8 plus, I'm going to write this stuff down, we'll put it in green. 8 plus, 2 minus, 3 minus, 3 times minus 1. Actually, put them up here. So if I take 8 minus 2 minus 3, that gives me an overall charge of plus 3. I've got 3 minus here, 2 times 3 plus, so plus 6, and nothing for water. So that gives me a plus 3 on my product side as well. It's really worth taking the extra minute or whatever it just took right there to double check and make sure that you are balanced for mass and for charge. It'll save you from making some careless mistakes. Since this concept is more complicated than anything we've talked about this unit, I want to take the time to go over another practice problem. So I'm looking at question number 2, the reaction between the permanganate and chloride ion to produce manganese 2 plus ions and the hypochlorite ion. First thing we want to do is assign oxidation states across the board. Pause the video, see if you can get the oxidation states. Check your work against mine. Hopefully assigning oxidation states is kind of second nature by now. This definitely classifies, or qualifies I should say, as a redox equation because the manganese and the chlorine are experiencing changes in oxidation states. Let's start off with a reaction involving chlorine. So I'll go Cl minus goes to ClO minus. Step 1, balance elements that are not hydrogen or oxygen. So in our case, chlorine. Chlorine is balanced. Then balance oxygens using water molecules. I've got 1 oxygen on the product side. If I put 1 water molecule on the reactant side, I've balanced oxygens. However, it's created a problem with hydrogen. I now have 2 hydrogen atoms on the reactant side. If I add 2 hydrogen ions onto the product side, I can balance for hydrogen as well. We should be balanced for mass now. Make sure we're balanced for charge. I've got 0 plus minus 1, so minus 1 overall on the reactant side, minus 1 plus 2, so a plus 1 on the product side. In order to balance that out, I'm going to add 2 electrons over to the product side. Let's take a look at manganese. Got the permanganate ion forming manganese 2 plus. Try this one out on your own. Pause the video, write the rest of the reduction half reaction, and then you can check it against my work. Check your work. How did you do? 5 electrons plus 8 H plus the permanganate ion yields Mn2 plus 4 water. Okay, we're to the point where we're ready to add our two half reactions. I've lost 2 electrons in oxidation. I've gained 5 electrons in reduction. Those numbers have to be the same, so I'm going to need to multiply each half reaction to get to the desired coefficients. If the coefficient of the electrons has to be 10, because 2 and 5, the lowest common multiple or least common multiple is 10, that means I'm going to have to multiply the first reaction by 5 and the second reaction by 2. So give me a second as I write all this stuff out again. 5H2O plus 5Cl minus yields 5ClO minus plus 10H plus 10 electrons. You really want to make sure your arrows line up. It's going to help make things a lot easier to cancel. So I'm going to do the product side first. It's going to make 8H2O. And I'll go back over to the reactants. I just do it this way to make sure I can keep everything in line and that I don't make careless mistakes. All right, I think I'm good to go. Add them together, we can start to cancel or partially cancel things out. 10 electrons on the products, on the reactants, 10 electrons on the products, those will cancel. H pluses, I've got 16 on the reactants, 10 on the products, get rid of all of them on the products, and I can turn that into a 6 on the reactant side. Water molecules, kind of a similar deal. We can get rid of all the waters on the reactant side. I had 5 of them. I've got 8 initially on the products. I can turn that into a 3. And I don't think there's anything else I can cancel out. So that leaves me with 6H plus 5Cl minus plus 2MnO4 minus yields 2Mn2 plus 5ClO minus plus 3H2O. My goodness, that is a lot of work. Before you celebrate that you're finished, double check for mass and for charge. 6 hydrogens, 3 times 2, 6 hydrogens, 5 chlorides, 5 chlorines over here, that's fine. I've got 2 manganese, I've got 2 times 4 or 8 oxygen on the reactant side. 5 plus 3 times 1 is 3, 5 plus 3 is also 8. We're balanced for mass. Not done yet. Check for charge. Let's write this in another color. I've got plus 6, I've got minus 5, and I've got minus 2 for a grand total of minus 1 on the reactant side. I've got 2 plus, so that's 4 plus. And I've got minus 5, 0. Gives me minus 1 on the product side as well. I am balanced. Yes, I know this is a lot of work, and I know that at first glance this looks extremely hard. But if you break it down into little pieces, start by assigning oxidation states. When you get to the half reactions, balance elements that are not oxygen or hydrogen first. Balance oxygens using water molecules. Balance hydrogens using hydrogen ions, H pluses. And then balance charge with electrons. Make sure that your electrons lost in oxidation and your electrons gained in reduction are equal to one another. If they're not, multiply the entire equation by whatever numbers you need. Anything you choose to do is really okay there. Add them up, cancel stuff out, check for mass and for charge. Again, I know this is hard, but I also know that you can handle it. So I hope you found this video helpful, and thank you for tuning in.